I'm Institute Paramita, and in this video I'm going to explain you nucleophilic substitution reaction. This is a very important topic which comes in every time. So SN1 we say nucleophilic substitution unimolecular, and SN2 that is your nucleophilic substitution bimolecular. So we will discuss about these two reactions. First we will understand what is a nucleophile. Nucleophile is an electron rich species. They may be neutral or negatively charged species. Nucleophile attacks on the carbon atom and displaces the leaving group. Okay, so it will attack, nucleophile will attack on the carbon atom and it will displace the leaving group. We have nucleophilic substitution reactions may be proceed either by direct displacement method, or you have indirect displacement method. Nucleophile, okay, if you have an alkyl halide, this is an alkyl halide where R is the alkyl group and L is your leaving group. Okay, so this one will attack, nucleophile will attack the alkyl halide, and the bond will break like this between nucleophile and then alkyl halide. It will try to break the bond, and then in the next step what will happen is that the nucleophile will take the position of the leaving group, and the leaving group will go out with its anion. Okay, so this is your direct displacement method. And you have carbon ion method, carbonium ion process. Okay, what is this carbonium ion? It is like when if you have an alkyl halide, what happens first, it will break down into alkyl plus and your leaving group, that is L minus. That means it will break the bond in the first position, give you a carbocation or carbon ion step. So this is called your carbon ion process, carbonium ion process. Okay, so this step is called the carbonium ion process, where this is also called the rate determining steps. And then the nucleophile, okay, whatever nucleophile you have in the reaction medium, it will react with this positive side of the alkyl halide, okay, to balance itself, and it will form like this. So this is the two types of, one is your direct displacement, it happens in a single step, and the other one is your carbon ion process. So the nuclear SN1 is usually the carbonium ion process, where there is a rate determining step will also be there. Okay, whereas your SN2 reaction, which we will study in further, it is your direct displacement reaction. It actually occurs directly, so we will say it in one step. So direct displacement reaction. Okay, now let us go for first we will discuss nucleophile and what is nucleophilicity. Okay, so nucleophilicity is nothing but, you can say, the reactivity of a nucleophile. So we will discuss reactivity of a nucleophile. Nucleophile means, suppose whatever nucleophile you have, when it is going to react with alkyl halide, so how much is it reactive? Is it reactive very less, or it is reactive a little bit more? Okay, which will be the faster in reaction, which will be slower in reaction? That will be determined by the nucleophilicity of a nucleophile. That is also called the reactivity of a nucleophile, is called its nucleophilicity. The nucleophilicity increases. So first we will see how the nucleophilicity varies. Nucleophilicity varies in different compounds. Okay, how we will see this in various periods and molecules also. So what is that? The nucleophilicity increases with the increasing basicity and polarizability. So now what you have to understand, what is your increasing basicity and your polarizability. That means nucleophilicity is directly proportional to basicity and also to polarizability. That means if something is a very good base in a nature, that means it can give electrons easily, that means we will say that it is a good nucleophile. That means it depends on these two factors only, that is the basicity. The more the basic, the more the nucleophile, the good nucleophile it is, the more polarizability. If suppose you go when the ion is little be suppose we take the case of I minus. Okay, I minus is also a nucleophile, but what happens is that as we go down the group, because of the electrons are higher in the subshells are more, that means the radius of the ion is more, the polarizability of the electron cloud is more, that means this will get polarized and try to form bond with the plus sign alkyl halide. Okay, so that times what happens, we said that if the polarizability is more, that means the nucleophilicity of that molecule is also more, hence it can form it can easily take part in SN1 reaction, or you can say nucleophilic substitution reaction. So what we will first one is that the nucleophilicity of an atom increases with increasing negative charge on it. Thus HO minus is more nucleophile, more, okay, then your H2O. Okay, here see HO minus, this is also a negatively charged, and this is water molecule. Okay, it also has electrons. Okay, it also has a pair of electrons to give, but see which one is will be more nucleophile. It is said the more is the charge, the more is the negative charge, the more is the nucleophilicity. Hence in this two, this one is greater nucleophile, good nucleophile than water molecule. Okay. Okay, now number 2, then we will see number 2 is that the nucleophilicity increases with the increasing atomic number down the group in the periodic table. Thus the nucleophilic reactivity of I minus is more than Br minus, is more than Cl minus, is more than F minus. Why it is said the nucleophilicity increases with the increasing atomic number, increases with increasing atomic number. Okay, increasing atomic number. Now see what happens is that as the atomic number increases, what happens, the size of the ion increases as we go down the group, the radius keeps on increasing. Okay, the more the radius increases, the polarizability is more, because the electron is in the outermost shell, it is highly polarizable. Okay, hence polarizability is more, so nucleophilicity is also more, hence nucleophile I minus is more good nucleophile than Br minus, then Cl minus, then F minus. Okay, now we will go for the third step. Decreases with the increasing atomic number along a period in the periodic table. Does the nucleophilicity of C more than N minus, more than O minus, and more than F minus. This is, you can say it is, this is an ion, carbon Cn minus, N minus, O minus, and F minus, they all have a negative charge, so they are also, you can say, they are nucleophile. But what happens along a period, if you go like this, your nucleophilicity decreases. Why? Because the atomic number will increase as we go along a period. See, it is in your group number 14, this is 15, this is 16, and this is 17. So as we go along a period, what happens, atomic number increases, and also the number of protons increases, so the number of electrons. So because the number of subshell is remaining the same, you are adding one electron, you are also adding a proton also. So the more you add proton, what happens is that this proton, the effective nuclear charge will increase, and it will try to pull the electrons towards itself. It will not allow the the negative charge to act as a nucleophile, rather it will pull towards itself. Hence Cn minus is a good nucleophile, then N minus, then O minus, then F minus. Similarly you can write these things in your copy as notes, because whatever I'm saying, it's very much important as notes. You don't need any other notes. So similarly, that of ammonia, NH3, is more than water molecule and more than HF. See, because see here NH3, ammonia also has nucleophile. Okay, this water also has nucleophile, this becomes F minus. But because we are going along a period, F minus comes in the 17, group number 17. What will it try to? It will try to retain F minus towards itself and complete its octet, then rather than giving it. So it is not a good nucleophile. Okay, it does not want to give. So nucleophilicity along a period. Okay, and ammonia is a very good nucleophile than water, then your F minus. Okay, number 4 is that living nucleophiles are usually I minus, more than Br minus, more than Cl minus, more than H2O, then N2 plus, then your Nr3, then your SO4 2 minus, then RSO3 minus, RCOO minus, NO3 minus, etc. Okay, this you just remember this. This is a, you can say, a sequence. Okay, the most polarizable and the least basic groups are generally good nucleophile. The most polarizable, okay, most polarizable, okay, leaving group, sorry, good leaving groups. Now see, in this case, what is that? The most polarizable, okay, and the least basic groups are generally good leaving groups. Leaving groups, that means the nucleophile which are leaving groups, that means they will easily leave the molecule, okay, to form other molecule. Why I minus will leave? Because see, it is down the as we go down the group, it is more bigger molecule, okay, so the polarizability is more, and polarizability is more, and also the the tendency of electron giving is very less, so it's very less basic. That means it is not willing to give electrons, okay, easily. It is more polarizable, it is not trying to give electrons, and hence they are generally your good leaving groups, okay. Then Br minus, then Cl minus, then H2O, N2 plus, N2 plus here, and R3C. These molecules, they have nucleophile, but because they have alkyl group and a bigger larger group, they are highly polarizable, and they are very less basic. They don't usually, they want to retain their electrons rather than giving it, so they are good leaving groups, okay. So you have to remember these types of nucleophile, they how they vary among a period, and along a period, then along a group, and also the nucleophile